of Final Products Chimorelli 2013.
FIC 2 Production Kanban Framework 3.2.2 Supply Kanban
Supply Kanban authorizes the travel of suppliers to deliver parts and components from a storage facility or warehouse to a manufacturing cell or workstation.
ขวงแอนคูซีแอป1996
Key information for Supply Kanban includes the number, description, and quantity of WIP that are delivered, supplier information, and stocking area after delivery. Chimorelli 2013.
Figure 3 Provide an example of Supply Kanban FIC 3 Supply Kanban Framework 3.2.3 Procurement Kanban
Procurement Kanban is related to the WIP parts that are stocking in the input buffers Gerger and Altidoc 2007. Specifically, it is a process of parts traveling from outside supply to the manufacturing location. Similar to Supply Kanban, key information of Procurement Kanban includes number and description of parts, storage location, or supplier information.
Figure 4 Provide a comprehensive example of Procurement Kanban FIC 4 Procurement Kanban Framework 3.2.4 Subcontract Kanban
The supply of orders obtained from subcontractors can ensure the influence of Kanban on inventory levels in the introductory phase as well as the balance between manufacturing processes within the work.
K Station Fukukawa and Hong 1993 According to Huang and Kusiak 1996 Subcontract Kanban authorized travel between different subcontracting units 3.2.5 Auxiliary Kanban Auxiliary Kanban is utilized to support extra work or backlog.
These kinds of Kanban can be issued depending on the order of the owners or on a weekly basic work plan. As a result, Auxiliary Kanban is issued separately to manage the planning and measure performance of additional work. Zhang and Kim 2007.
Auxiliary Kanban can be issued in the form of Emergency Kanban, Express Kanban, or any specific type based on the requirement or situation. Huang and Kusiak 1996.
There are some examples of the equipment that can be applied in the auxiliary Kanban such as Kanban box collecting Kanban after withdrawing.
Kanban Management Account Managing Kanban Implementation
Supply Management Account managing raw materials supply and dispatching board displaying schedule of production.
4 Benefit and Drawback of Kanban System 4.1 Benefit of Kanban
According to Jody and Rao 2012, the implementation of the Kanban system is a major source of achieving competitiveness, which provides the following advantages. Enhancement of customer satisfaction and retention rate for business. Promotion of international trade, improvement of quality, efficiency, and effectiveness of the operation. Improvement of employees' attitude, motivation, and awareness. Development of adaptiveness and flexibility. Prevention of overproduction and elimination of waste.
Reduction of cost.
Increase of productivity and profit margin. Furthermore, Gross and McGinnis 2003 provided slightly different research on the advantages of the Kanban system. Specifically, they identified 8 different benefits, as discussed below. Cutback in inventory, enumeration of the operation flow, prevention of overproduction, enhancement of control at the operation level, material handling level, development of process management and visual scheduling, improvement of adaptiveness and flexibility, minimization of inventory obsolescence risk, enhancement of supply chain management.
4.2 Drawback of Kanban
In spite of several advantages, there are certain disadvantages of Kanban implementation in the manufacturing industries, which are discussed below. Kanban is less effective where the resources are shared or sudden change in the demand in the downstream. Product mix or demand changes may cause problems.
The Kanban system does not eliminate variability.
Production flow problems with poor quality products or products with a wide variation such as fashion and textiles cannot be used independently as it needs other tools such as JIT or 5S. Time-consuming process as the impacts are realized after a long time.
Implementation of Kanban
5.1 Fashion and textiles industry applications. There are key determinants to evaluate the effectiveness of the Kanban system in the manufacturing industries such as fashion and textiles. NIAC 2020. For example, in the fashion and textile industries, measuring the effectiveness of increased output from qualified inventory management, correlation of supplier activities and production lines, ensuring quality improvements and quality control, and maintaining employee devotion and employer commitment is rather a difficult task. However, these are the highly relevant factors defining the success of an industry after the implementation of Kanban. 5.1.1 Increase output from qualified inventory management. Without appropriate inventory management, a cost-efficient strategy can never be acquired. Heiser and Render 2005. For these authors, inventory management can be divided into 4 areas of management. Namely, raw material, work in process WIP, finished products, and processing, maintenance or repair inventory. With a close correlation to the holding costs and storage in manufacturing plants. Inventory management can be impacted by the volatility of real-life demand by external parties. Kabasi and Liang 1999. Due to the application of Kanban systems with a high level of flexibility, an industry, especially in the inventory management process, can respond quickly to market changes. Assess each task comparatively and concentrate on an ultimate goal to gain a competitive edge. As the fashion and textile industries use a large quantity of inventory, the Kanban system can help in the effective inventory management. 5.1.2 Ensure supplier participation correlate with the production lines. The application of the Kanban system only demands a certain inventory capacity that adapts the production numbers. Specifically, compared to the just-in-time JIT management, the Kanban system performs in a wider scope, in which not only the production and supplier scheduling are fine-tuned, but also the invento. RI is always kept to a minimum level with closely monitored production and WIP. Donald 2003. That given, supplier commitment in fashion and textile industries is important to ensure efficient and smooth production lines, and therefore, 5 criteria of opting for a qualified supplier include up to standard quality, willingness to cooperate, and competency in technical, geographical, and pricing aspects. 5.1.3 Ensuring quality improvements and quality control. Low standard operational quality in a business may result in lower costs but will also cause a higher level of defects. Ballram 2003. The fashion and textile industries suffer from the problem of good quality products in several instances. The implementation of Kanban system can ensure a better cost-saving process by managing inventories and quality improvements in output. JIT is important to evaluate the total quality management (TQM) system. Flynn et al.
1995
A JIT is considered effective when a business achieves a certain level of quality standards before being confirmed in a continual operation intended to reach customers, which ensures a competitive advantage that high quality affords the business processes and consumers without any prevention, appraisal, and failure costs bias. Bernstein 1984. Hence, by ensuring quality improvement and control through minimizing waste from incorrect work, over-processing, and space-consuming execution, the Kanban system brings greater efficiency to a business.
as a whole.
5.1.4 Maintain employee devotion and employer commitment. By provision of improved visibility and problem solving, the Kanban system assists employees to visualize task divisions and allocate responsibilities appropriately, quickly identify problems and offer
solution.
From those advantages, a business can enhance employee participation and management to achieve the final objective of providing incentives and thereby ensure a loyal, cooperative, flexible,
and dedicated workforce.
This approach is beneficial in the fashion and textile industries to improve the employee devotion as well as employer commitment.
5.2 How Kanban Support Fashion and Textile Industry 5.2.1 Case Study 1 Kanban Application by Zara.
In this case study, Zara, one of the biggest global fashion retailers from Europe, implemented the Kanban system for its inventory management process. Specifically, the brand had chosen to concentrate on a low stock-based approach, i.e., reduced inventory level, relying on the pull system to quickly adapt to customer trends with new designs introduced monthly. The digital Kanban system was utilized to closely monitor the production efficiency of Zara's partners in other countries, in which the data was better tracked by catching signals from multicolored lights. Red refers to a machine stopping or breaking down, purple for changeover, blue for maintenance, and green for availability, and the data flow was monitored overall. With the application of Kanban in the manufacturing and supply chain of Zara, the inventory turnover of the brand was maximized. Zara also adopted the Kanban system to mitigate its inventory holding costs and control shortages of inventory. In detail, the system was implemented in all the warehouse levels of the brand located in Europe and other locations. As a fast-changing brand adapting quickly to customer fashion preferences, Zara emphasized the Kanban role in manufacturing, sourcing, design, and distribution to the retail process almost all over the
world.
Specifically, the system has been effectively applied in over 300 small factories across Morocco, Portugal, Turkey, and Devon, Asia. Eventually, certain benefits were achieved by Zara as a success as discussed below. Better monitoring of production flow. With the application of multicolored lights in the digital Kanban system, defects were easily detected, with detailed identification of where they occurred in the process. The supervisors and workers can easily view the different colored light and can take action accordingly. For example, a worker can observe the red light when there is a machine stoppage and quickly fix problems so that the machine can be brought to working to improve the productivity and reduce the wait.
In time.
Improved production flow with on-time information. Another benefit stemming from the digital Kanban system was that the performance in a diversity of production flows were all controlled and ensured the same performance rate. This on-time information availability also meant that any malpractice noted from the flow was quickly examined and corrected so that the flow could be turned back to its normal performance stage. Through these two benefits, the efficiency of the brand Zara was increased to a level of 100%, a statistic that many industries, especially the fashion and textiles industries, could strive to emulate. The implementation of Kanban can bring the efficiency to a 100% level. 5.2.2 Case Study 2. Kanban application in a shirt manufacturing industry. In India's shirt manufacturing industry of an Indian domestic retailer acquired in-house manufacturing for clothing types varying from shirts, trousers, blazers to suits. With a production capacity of up to 2,500 pieces per day, the industry acquired 10 departments executing the steps as shown in Fig. 5. The various departments included Production Planning and Control (PPC) Department, Fabric and Trim Store, CAD Computer-Aided Design and Pattern Making Room, Cutting Room, Fusing Room, Embroidery, Part Preparation, Assembly, Finishing and Packaging, and Dispatching Shipment Department. Fig. 5 Process Flow Chart in the shirt manufacturing industry in India. Before, the industry was following the traditional manufacturing practices, which lead to several problems: higher lead time, excessive inventory and delaying of orders. Specific problems were identified at each of the above stages and are detailed below. Delayed orders. Because of a lack of communication between management and supervisors when deciding on the prioritization level for each order, some orders were totally ignored. This resulted in delays in production as well as customer dissatisfaction when orders were not available on demand. Excess inventories in WIP. Since the whole production process was not unified, the industry suffered from an increase in WIP and inventory. Unpredictable production. Since the departments and management decisions were not unified, the production floor lost track of upcoming and processing orders. This created less predictability and involvement in production. Specifically, as each line only paid attention to producing more pieces regardless of particular orders, the management board found it more difficult to predict accurate statistics. More concentration on the push system. The industry was paying more attention to pushing its products to consumers rather than pulling what the customers were really demanding. After these problems had been identified, the Kanban system was implemented, especially at the cutting, sewing, and finishing stages. The object was to enhance the production process, improve communication, and involve staff at all levels in the overall management of the business. Specifically, the system provided information regarding weaknesses in each process, orders that were being produced, and orders that were in most demand with a certain required quantity. From that information, excessive inventories, lead time, scrap, and rework were considerably reduced. This in turn increased flexibility, made the production process of the business much more transparent, visual, and predictable. Implementation of the Kanban system moved the business to a more demand-driven production process. As a result, the production process was allocated within a more structured framework, and output was increased by 20. Inter- and intra-department communication was also enhanced and more effective, which reduced WIP by 30%, minimized idle time in operations with less waiting time, The space occupied was also released by up to 50% with better inventory management.
6. Conclusion.
In conclusion, this chapter has discussed the fundamental principles of Kanban system and its implementation in the fashion and textile industries for enhancing efficiency. Kanban systems are based on the use of signals in manufacturing industries to control the movement of goods in the production floor. In Kanban system, a pull system is followed to produce as much as quantities which are actually in demand. Kanban system uses the JIT approach, which means each process in the manufacturing line pulls the number of components in the next process just at the right time. As a major tool in the lean manufacturing process, the Kanban system has been designed to help the workflow as agile and efficient as possible through the utility of visualized signals is different.
Color light.
Compared to the traditional system, Kanban system has been considered more efficient in reducing the bottlenecks by visual signaling.
Depending on different type of material handling, the Kanban system may be separated into 3 control systems, namely single Kanban system, dual Kanban system, and semi-dual Kanban system in fashion
and textile industries. The Kanban system has undoubtedly brought about a positive impact in several developing countries. Some case studies have been presented for the fashion brand Zara and the shirt manufacturer from India. It has been shown that the improved management of inventories, raw materials, semi-finished products, WIP and finished goods, the system has helped businesses to mitigate waste
and aim for a zero-defect
production line, in which the quality is strictly maintained right from the initial source to delivery of the final product to the customer. Kanban implementation specifically, as a lean manufacturing tool, perform as a great support to the fashion and textile industries.
Reference Rambi 2003 Kanban System Bettering andเครื่องหมายสงวนลิขสิทธิ์ The Author S Under Exclusive License to Springer Nature Singapore Ltd 2022 นัยยักษ์ S
Lean Supply Chain Management in Fashion and Textile Industry Textile Science and Clothing Technology
https://doi
org 10 17978 981 192108 7_9 Other lean tools in fashion and textile manufacturing
ที่เอฟคองฟัม1อีแฟนอุลาก1พอลเยโอ1แอนโมฮัมมัดเรซาแอกบารี1 2
This chapter discusses how waste reduction, process efficiency and safety in textile manufacturing can be managed using lean manufacturing tools, namely MUDA, Six Sigma and statistical process control. In addition to ergonomics,
MUDA approach identifies 7 waste group in post-implementation manufacturing process.
The chapter highlights 4 MUDA techniques to perform the waste identification, including building lean thinking and cultures, hybrid approach of combining multiple decision-making methods,
integrating
lean and green management, and value stream mapping to prioritize responses to wastes. Statistical process control focuses on process deviation in manufacturing and provide a real-time analysis to enhance the future production predictability. Six Sigma is a process-based strategy consisting of 5 stages: DMAIC: define, measure, analyze, improve, and control, used as a data-driven process to eradicate defects in manufacturing process. Finally, ergonomics, which focuses on interactions among humans and other elements of a system to optimize human well-being and overall system performance, is recommended to combine with lean manufacturing to improve quality and well-being of workers in textile industry. Keywords: Lean MUDA Six Sigma Statistical Process Control Quality Management Tools Ergonomics
1. Introduction
Fashion and textile industries create an immense global market that influences the economy of almost every country, either directly or indirectly. Despite its extensive size, rise in the global business, the industrial sector still faces many challenges. It traditionally experiences low productivity, labor-intensive, manual work practice, high product defects, and inaccurate demand forecast due to fast-changing apparel styles. Karthikadevi 2014. The industrial sector is under pressure to focus more on effective and efficient manufacturing processes for survival in a highly competitive market. Minimizing production wastes, product defects and labor idle time are some key conditions of reducing cost, increasing productivity, and adequately focusing on high-value added activities. Akbari and
ذو 2021 أكبر عندها 2020
wastes, which can be any excess in materials, components, or equipment in the manufacturing process, can be traced to various stages. Lean manufacturing comprises a number of principles and techniques aimed to eliminate wastes and reduce low-value added activities at various stages of production or services to achieve high quality and competitive products or services. For Koch et al.
2016 Hodge et al. 2011 Petersen 2009
The focus of lean manufacturing is considered as a managerial approach rather than a set of tools to improve business performance based on the integration of socio-technical system. Angelis and Fernand.
ES 2012 Bortolotti et al. 2015
This chapter presents three main approaches in lean manufacturing, namely, MUDA as a waste identification technique, Six Sigma and statistical process control for process performance improvement, and their applications in fashion and textile manufacturing. Besides, the issue of ergonomics in the manufacturing is also covered, as it can have a significant impact on the improvement of working quality and well-being of workers in the industrial environment.
2 Muda in Lean Manufacturing 2.1 Overview Muri, Mura and Muda are the three waste reduction technique proposed in 1950s by Toyota Production System, Model 1983.
Out of the three, MUDA focuses on the identification of production wastes after the process has been put in place, helping businesses to accurately identify either socio or technical aspects that need improvements and develop appropriate strategies to adjust and optimize production processes. Shama 2013.
Wanesek et al. 2018
MUDA focuses on 7 major wastes of business operation, including transportation, inventory, motion, waiting, overproduction, overprocessing, and defects. For Koch et al.
2016 Benam et al. 2018
Although initially discovered and applied in the Japanese automotive industry, MUDA approach can be adapted for different business types to better identify potential wastes or factors that cause wastes.
of the business operation or processes. Wanesek et al. 2018
Furthermore, types of wastes can be added to provide a more complete representation of the business waste management. English 2005, Sutherland and Bennett 2008. The next section will expand the types of MUDA wastes and how the MUDA waste technique has been applied in several industries. Waste identification have been explored in different industries, such as in managing information. English 2005, in supply chain SC management. Akbari et al.
2017 Sutherland and Bennett 2008 in clothing manufacturing. Benam et al. 2018 and fast food industry. Morel Contreras et al. 2020
The general definition of 7 deadly waste elements of MUDA can be explained as below. Transportation, time, resource wasting and other costs that are generated from unnecessarily moving products or materials. Inventory, the excess of materials or products that are not processed. Motion, wasted human efforts and time for unnecessary works. Waiting, the time spent on waiting between processes steps over production, making more products than demand or required. Overprocessing, wastes from higher requirement of quantity and quality of works than needed. Defects, wastes from a product, service, process's failure. The nature of each waste element can vary subject to industry characteristics or types of product, service provided. For example, overproduction waste in information management can include redundant systems, duplicate records, or hidden information storage, whereas in SC management it relates to higher order quantity than needed. In clothing manufacturing it can be the number of unsold products after a sale period, or in fast food industry it indicates over number of cooked meals or finished goods inventory. Waste sources can be either eliminated or identified and reduced depending on business nature. When discovering waste factors in managing information, English 2005 added 2 new elements, including repairs, rejects, and wrong decisions. While Sutherland and Bennett 2008 added space element as a supplement waste element in SC management. On the other hand, Sutherland and Bennett 2008 eliminated over-processing waste in SC management, and Morales-Contreras et al. 2020 dropped the over-processing and motion-wasting element in the fast food industry. The name of the waste element can be also modified to better fit with the business context. Defects was called process of failure in information managing, English 2005. Or errors in SC management, Sutherland
and Bennett 2008
Multiple methods have been developed to apply MUDA in lean management to identify waste sources in business operations or processes.
MUDA method can include 1. Building Lean Thinking and Culture, Sutherland and Bennett 2008, Tama 2013, to promote and adopt lean management approach. 2. Hybrid strategy such as Pareto analysis.
Or 80-20th principle, decoupling points, separation between base and surge, demands to integrate lean and agile approach to deal with uncertain business environment, Christopher and Twill 2001, 3. Integrating lean and green management approach to minimize wastes by combining 3R, reduce, reuse and recycle hierarchy with deadly wastes of lean management, Furcock et al.
2016 and 4. Using Value Stream Mapping, Benham et al. 2018 and 5. Analytical Hierarchy Process, AHT, and FTSE AHT, Yanavel Babu and Aran Ejiri 2018, to more fully and accurately identify sources of waste and prioritize responses.
Each of these methods will be further explained in the following sections. Acquiring lean thinking and culture has been identified as a core competence in effectively implementing lean approach and application of the MUDA, Shama 2013. Christopher and Twill 2001 emphasized the important role of senior executives in the lean culture development. To ensure that everyone is aware of the various forms of wastes and solutions to eliminate the wastes, senior executives need to regularly observe the employees' working activities.
Develop the problem
solving capability by asking the 5 whys questions. Womack and Jones 1996 proposed 5 principles that firms should follow to develop lean culture and achieve the overall value creation. 1. Identifying customer value. 2. Managing the value stream. 3. Developing the capacity to flow production. 4. Applying a pull system to support the flow of materials to constrained operations. 5. Detecting excellence by eliminating all forms of waste in the production system. Similarly, Shama 2013 suggested 6 fundamental tasks to promote sustained and organization-wide efficiency and waste reduction. 1. Planning for change. 2. Designing suitable strategies and procedures to support lean operation. 3. Implementing the suggested plans, measuring employees, departments or organizations' performance. 4. Analyzing defects, lean from leaders or feedback to create a knowledge base to achieve optimum performance by eliminating waste. 5. Exceeding customer expectations, and 6. Adding value to stakeholders. These lean principles and tasks help managers or even employees in tracking the degree of leanness in all business parties and activities. However, this process needs to be implemented with sensible consideration of negative impacts on employees' morale or work and life balance. It might lower the employee performance if they perceive it as unnecessary, time-consuming, and feeling stressed because it might indicate redundance in an employee's position. Thus, suitable actions and decisions from managers or senior executives are important in successfully generating and maintaining leanness among employees and business activities. The separation between the agile and lean management is debatable. Some prior studies indicated that there is a fundamental difference between these two concepts, whereas others showed possible integration and common effects of both methods on the business operation. Christopher and Twill 2001 indicated 3 hybrid strategies in order to integrate lean approach within agile SC management. The first strategy is the Pareto curve approach with the rule of 80-20ths, in which 80% of total volume will be generated from just 20% of the total product line. Christopher and Twill 2001. Lean approach should be applied to the top 20% of products by volume, which is predictable, whereas the other 80% which are less predictable are where the agile management approach should be applied. Secondly, another suggested hybrid strategy is the decoupling point or strategic inventory approach, Christopher and Will 2001. This approach suggests that companies can apply lean method to effectively manage the holding materials, which is predictable, and only complete final assembly when customer requirements have been
Format, which require agile management approach.
The transforming point between these two methods is called as decoupling point. Another lean and agile hybrid strategy proposed by Christopher and Will 2001 is the base and surge demand separation, in which the business can put customers into base demands,
which are more like
to be forecasted and managed by the lean approach, and surge demand, which are less predictable and managed by agile management approach. Based on these demand differences, organizations can distribute the manufacturing capacities to both reduce costs and ensure the flexibility to match customers' needs. Each of these hybrid strategies is suitable for different types of market conditions. For example, the Pareto analysis or 80-20th strategy is better used in an environment that has high levels of variation in customer demands, while the decoupling point strategy is suitable with market conditions of modular production or intermediate inventory, and surge and base demand separation strategy is suitable when the base demand can be predicted confidently for applying a lean approach and putting local manufacturing available for applying agile approach. In other words, under a dynamic environment, lean management can reduce wastes
e.
Muda through the implementation of the agile management. Another tool designed to minimize the 7 deadly wastes in Muda is the Lean 3R matrix by Furcock et al.
2016.
In this matrix, each of the 7 wastes from Muda is linked with the 3R items, including reduction, recycle, and reuse, to better identifying the wastes and deciding the solutions to eliminate them. The 3R hierarchy provides a process that includes 3 steps of eliminating wastes. The first step is to identify and quantify the waste sources. At this stage, the 7 Muda concepts from the lean approach can be applied to provide a full and accurate overview of waste identification. Second step involves analyzing the effects of the identified wastes on the business performance. In the final step, the managers decide whether to reduce, reuse, or recycle the wastes and formulate a detailed solution to implement an appropriate waste minimizing method. The Lean 3R matrix showed a positive result in minimizing the wastes, following the 7 Muda, and improve the environmental performance of the business operation. The 7 Muda elements server is a checklist that allows managers to assess wastes that might exist from the business operation, whereas 3R hierarchy provides directions for analyzing the potential causes, effects and minimizing solutions of identified wastes based. Another focus of Muda is to accurately identify the 7 deadly wastes in business operation by classifying the chain of operational activities into separate stages, then identifying potential wastes at each operational stage or activity under different working scenario,
i.e.
stable or uncertainty working environment, which can be done through value stream mapping.
Benham et al.
2018 proposed the use of value stream mapping as an efficient tool to detect the 7 wastes. This mapping tool allows the managers to obtain an overview of the production process, from importing raw materials to transporting finished products to customers.
For example, study of Benham et al.
2018 broke the shirt sewing production into 20 separate activities, then classified them into 5 stages, including cutting stage, sewing stage, enzyme stage, quality control and ironing stage,
and
barcoding, folding and warehouse transportation stage. Then, the potential wastes in each activity were identified and categorized according to the 7 deadly wastes. For instance, at the cutting stage, several wastes have been identified, such as cutting wastes classified to defects, element cutting workers movements classified to motion, element delay in the fabric delivery from supplier and delay in fabric cutting classified to waiting, element and cut fabric stock classified to inventory, element. Based on this mapping tool, managers can review and identify wastes at each small stage in a large production process. Furthermore, each of the identified waste will be classified by their consequence in either delaying time or financial expenses. Thus, Muda can provide the managers an accurate overview of the wastes in the production processes to develop an efficient waste minimizing program. The wastes in the entire production process, therefore, can be fully discovered, helping managers to provide appropriate and effective waste minimizing programs or strategies.
ยานาเวลบาบูแอนอารันเอจิรี 2018 Proposed AHT and FITSI AHT Algorithm in Segregating
Measuring the weights of 7 deadly wastes and prioritizing responses. The aim of both methods is to break down a lean problem into smaller components. AHP helps the managers to focus on a limited number of lean wastes using weighted rankings in each stage. Fuzzy AHP can consider the uncertainty in the environment and the response's deviation, hence providing more accurate prioritization among lean wastes. Both methods showed a good result in helping managers to assess waste elements and to identify the major wastes. However, the Fuzzy AHP method showed a better performance in measuring the lean wastes and solving the multi-criteria decision-making problem. 2.2 Muda application in fashion and textile industry. Several studies examined applying 7 deadly wastes of Muda approach to manage and eliminate wastes in the fashion and textile production systems.
For example, Benham et al.
2018 proposed the value stream mapping approach as a tool to identify and prioritize production systems Muda in clothing manufacturing companies. Because Muda from different process stages might relate to each other, hence eliminating of all wastes one time can be difficult. Value stream mapping tool allows the manager to break down the whole production chain into separate stages and identify the potential wastes in each production stage. The managers, then, can measure the impact of time and financial expenses of each waste separately and decide waste reduction responses. In their study, 40 potential wastes have been identified from 20 production activities in 5 major stages. 3 wastes in waiting stage accounted for 2.79% of total wasting expenses, 6 from motion 0.58%, 4 from defect. 74.5%, 2 from overprocessing, 1.41%, 1 from overproduction, 2.04%, 6 from transportation, 2.14%, and 18 from inventory, 16.54%. The managers, thus, can decide which wastes they should focus to eliminate to bring the most efficient improvement in production process. For example, 20 out of 40 identified wastes accounted for 97% of the production inefficiency, whereas the remaining 20 contributed only 3. Managers should focus their resources on addressing high-impact wastes, instead of spending resources on minimizing less important wastes.
3 Six Sigma and Statistical Process Control 3.1 Overview
Over the years, firms have started adopting quality management tools at operational and strategic level to enhance their supply chain capabilities and overcome the performance dilemmas. Six Sigma and Statistical Process Control (SPC) methods are a part of Total Quality Management (TQM) improvement programs, and its techniques are widely embraced to monitor and discover process variations in manufacturing and supply chain process performance (Niastani 2017). Moreover, these tools become a complete integrated system of information sharing and knowledge management tool (ANI et al.).
2017
To the same degree, SPC is also helpful in delivering right results required by the end market and customers. Supporting management to decide on suppliers' performance and ranking them as preferred suppliers, and developing a systematic approach conclusive evidence to supply chain level strategies as part of organization-wide strategies.
Tahin et al.
2010 conducted an exploration to develop an integrated roadmap of quality management by combining the traditional 7 quality tools and new quality tools as well. However, majority literature suggests Six Sigma and SPC application largely limited to large enterprises, as well as more explorations are required in SMEs, small and medium-sized enterprises, and in developing countries.
3.2 Statistical Process Control DRW
Edwards Deming endorsed the idea of statistical rationale as part of organization process management strategy. Today, Deming's approach is established as part of quality management strategies in many firms to enable process insights in reducing variations, Setti et al.
2020
SPC is defined as a managerial toolkit using statistical methods to monitor and control manufacturing processes data to ensure that the outputs conform to specifications. SPC is a practice based on Schuhart's conception of process variability, which is widely applied not only in manufacturing processes but also in service operations. Compared to inspection method, Madanhire and Emboa 2016 establish and extend SPC as a lean tool by detecting and minimizing errors whilst developing a product according to conformance standards. SPC is further designated as a major tool for sequential process monitoring to ensure operational adequacy such as production lines, customer services issues, improper use of raw material,
and operational
related errors. DOS 2013. In the 1960s, Kaoru Ishikawa advocated the idea of quality management using statistical tools named as 7 quality tools.
Nat and Guageta 2001
The aim of these tools was to enhance the team and workforce capabilities by utilizing staff skills in business process improvement.
Several tools could be attributed as process quality control to including Pareto chart, cause and effect diagram, or Ishikawa diagram, scatter diagram, flow chart, histogram.
Check sheets and control.
Chart, Muhammad 2015
However, in fashion and textile industry, majority of studies have commonly used only 3 major tools, namely Pareto analysis, cause and effect diagram and control charts. Oda et al.
2020-2013 et al. 2007 Hodgson al. 2017 Majumdar et al. 2012
The following section provides a brief elaboration of commonly used quality control tools in fashion and textile industry. SPC tools and methods can be applied in 2 phases. During the first phase, often control charts are developed by plotting data to uncover and understand whether process is under control. By analyzing the control charts, inbound and outbound, one could identify the potential causes of variations. By incorporating other tools such as Pareto principles and brainstorming sessions are conned.
to make process adjustment, Madana and Emboa 2016, Masan and Anthony 2000.
Secondly, understanding the process capability is key to quantify the capability of the studied process to produce products that could meet required product specifications. The second phase covers the process capability by calculating capability indices of the processes mentioned by Mason and Anthony 2000. The pre-defined specifications defined customers as the lower specification limit (LSL) and important tasks as the upper specification limit (USL). For an organization to comply with the limits that brings
Return and benefit to NA 2018 Pareto analysis or ABC analysis.
Often named as 80/20ths rule, is a common method deployed to categorize the performance or outcomes to understand the variances from different angles. Pareto principle is based on the idea that 80% of all problems, production or supply chain in this case, could be solved by removing the causes related to 20% of all problems. Mock and Wiketa 2001.
Wang and Zhang 2008.
Studies in the fashion and textile industry shows positive impacts of Pareto analysis.
As shown in the Atta et al.
2020 study. Pareto analysis helped the firm to quantify the problems in denim washing process and found that out of all the causes, only 5 categories, namely chemical repair, blue floor, chemical intensive, light floor and deep floor defects accounted for 78.6% of the total 53 washing defects. In another study involving a yarn manufacturing industry in Bangladesh, the application of 80/20ths rule established that among all production and manufacturing losses, stoppage losses contributed the most at 67% compared to breakdown losses of 22%. Hassan et al.
2017.
Cause and effect or Ishikawa or fishbone diagram is one of the systematic approaches to brainstorm causes. Liliana 2016. This diagram represents causes related to a specific process or event. The diagram became popular in lean management in identifying root causes of a variety of problems. Hassan et al.
2017.
Fishbone diagrams can shed insights and support in brainstorming to identify possible causes of a problem and in sorting ideas as feasible solutions, thus being a useful tool to explore process abnormalities from multiple factors. Liliana 2016. In a study conducted on textile industry washing defects by Oda et al. 2020, cause and effect diagram facilitated to categorize causes of defects into 6 different categories in denim fabric washing. This study also found majority of causes emerged due lack of color experienced staff at different stages during denim fabric washing. Moreover, chemical defects could be associated with defects in the color category. Oda et al.
2020.
Process control charts or P-chart is a graphical diagram supporting process control by drawing and pointing in out of control of a cause. Values Muhammad 2015, Mach and Wiketa 2001. Control chart provides controlling graphics of all attribute values that indicate if process is kept under control, or the values are exceeding upper control limits. Auta et al.
2020
Upper control limit UCL shows the maximum value as acceptable variation from the average value on the process. Lower control limit LCL is the minimum value acceptable variation from the average val. U of the process and central line CL is average value on the control charts. P-charts could help firms to predict the performance of a process in the long run. Therefore, process control charts can serve as a preventive tool to further research and develop necessary corrections if a process is out of control. DOS 2013. Check sheet is a simple form that allows employees and operators to record data and information in a systematic manner. A check sheet captures specific events of a process frequency in a consistent and economical manner. Niastani 2017. Data captured from these events could be rearranged for future reuse, but check sheets are not seen as a prominent method of problem analysis. One type of check sheet, for example, is tally sheet, which is a very basic tool in the form of counting the occurrences of a specific event. 3.
3 Six Sigma concept.
Six Sigma is a systematic strategy to quality management and was coined and formalized in 1980s by Motorola, Horrell 1998, Mach and Wiketa 2001. Since then, Six Sigma is found one of most effective management approaches, which has helped many Fortune 500 firms to reap benefits by increasing market share, healthy cost reductions,
and dramatic EF.
efficiency enhancements by optimizing business processes. Harry and Schroeder 2000. Following the TQM philosophy approach to zero defects, Six Sigma's major goal is to diminish inconsistencies and continuously meeting customer expectations over time. Mach and Wiketa 2001. Sigma, standard deviation from the mean, measures the variation of a process from its mean value. Since a major aim of Six Sigma is striving for zero defects, a value of 3.4 defects per million opportunities is allowed to achieve the lowest probability of an error. Horrell 1998. 3.4 Six Sigma 5-stage process. Six Sigma is a process-based strategy consisting of 5 stages: define, measure, analyze, improve and control. DMAIC. During the define stage, a firm needs to establish the goals and scope of the improvement activity at project and operational quality levels. In addition, during this stage a project charter is also developed, and project teams are identified. Hassan et al.
2017
The measure stage requires a project team to identify the relevant parameters and past information to measure the existing performance of a process. Horrell 1998. For example, machine usage, current product quality levels, fabric's shade, dyeing requirements and length of the fabric set C are some of the parameters. DOS et al.
2007
It is necessary to establish the matrices and KPIs, key performance indicators, to monitor the future goals.
E. Developing the baseline values and target sigma level.
During the analyze stage, current process or system-related root causes are traced. Often in this stage statistical tools are used for root cause analysis. DOS et al.
2007 Matt and Guageta 2001.
Furthermore, a project team could use the brainstorming sessions and develop the cause and effect diagrams to visualize the defects from different perspectives. Chong et al.
2012 Coel 1998.
The main goals of this stages are to develop a shared meaning, researching the root cause of actual issue, and to establish key actions on the decision-making. DOS et al.
2007
The improve stage requires the project team to operationalize the decisions towards a solution for the root causes identified during analysis phase. Mach and Wiketa 2001. During this stage key improvements are made through feedback and prototypes development. The solutions are finalized once the sigma level established in the start of the project are achieved. Mach and Wiketa 2001. These changes could be from simple to more innovative implementations, including process change, change of dyeing process or quality level of the color. DOS et al.
2007
Control stage is the final stage of a Six Sigma project. The goal of this stage is to sustain the achieved results. Mach and Wiketa 2001.
Das et al.
2007 exemplified three main points to be addressed during this stage: development of a change control plan and structure, new knowledge transfer of process changes to staff, and document and report. Ing of unattended issues during the project for future improvements. Six Sigma is conducted on a project-based approach to remove waste and process improvement.
Chang et al. 2012
As majority of studies employing Six Sigma as a data-driven process to eradicate defects, SPC tools are often found to be a subset of Six Sigma. The real essence of Six Sigma is employing DMAIC method, taking all SPC-related tools at different stages along the process. Chong et al.
2012
Six Sigma uses a systematic cycle problem-solving methodology. SPC used statistical procedures at each phase during the manufacturing process to identify and tracking of errors and variations. Both approaches help firms in coping with the quality variations on operations in supply chains and support managers to further design experiments to explore critical factors affecting process and
D
quality that could lead to best possible performance. Evans and Lindsay, 2002, highlighted three statistical principles of continuous improvement. All work occurs in a system of interconnected processes. Variation exists in all processes, and understanding and reducing variation are keys to success. 3.5 Six Sigma and SPC in fashion and textile industry. Process parameters in supply chain and manufacturing could deviate from their base values due to some chance variations. SPC tools could offer a great real-time analysis and enhance the future predictability by analyzing data in supply chain and logistics-related processes. DOS 2013. However, developing and adopting these methods comes with a greater risk from different perspectives. Although several studies found positive impacts of SPC in the manufacturing industry, its applicability in fashion and textile industry requires more academic work. Madanhire and Embowa 2016. Previous studies show that SPC offers an advantage on assessing the detection and corrective action against the operational problems in supply chains. Seti et al.
2020 Wang and Zhang 2008 Eni et al.
2017 developed a quality control system for apparel production SMEs in Indonesia. This study concluded that the SPC as an information system with mobile platform could effectively contribute to feedback and knowledge transfer for fashion and textile experts.
In the garment industry, SPC technique including flowchart,
Pareto analysis and fishbone diagram help to analyze current process, and with historical data help to understand the nature of the mistakes during the production process. Tuna 2018. Shafira and Mansur 2018 applied Six Sigma in production quality improvement analysis of gray cambric in a textile setting. Using a waste assessment model (WAM) approach, they explored the frequency of different types of production waste results. They found that production defects, inventory, motion, transportation, overproduction were the highest among other categories ranked. The analysis revealed a level of 3.3 sigma lower than the average Japanese firm. FMEA, failure mode effects analysis, and AHP was also used to understand malfunctioning of machines. Moore and Pawar 2015 survey on 26 textile companies in India found that textiles companies only use ISO 9000 quality management system. Moreover, this study stated that Six Sigma is not given importance as a quality tool in several industries. Using a case study method in the South Indian textile firms, Karthi et al. 2013 also found the ISO 9000 implementations are common among the firms. However, companies seldom try Six Sigma as a tool of their quality drive. Tainer 2012 investigated the critical success factors of Six Sigma adoption in Turkish textile SMEs. Using a survey-based approach, this study found involvement and commitment of top management linking quality initiatives to employees. Information technology and innovation are found to be important success factors for Turkish textile SMEs. In addition, leadership and commitment of top management, strategic vision, data collection and measurement are found to be the most CSF's critical success factors for the successful initiation of
Six Sigma program.
Furthermore, the lack of knowledge of the system to start the initiative and the presence of ISO 9000 certification in SMEs are found to hinder its implementation of Six Sigma. Results of this study also concluded that personnel and incompetency with new technologies are among the failure of implementation of Six Sigma in SMEs. The above review has shown that SPC and Six Sigma could help fashion and textile firms to overcome several quality and waste management issues. But recent research highlights that majority of firms apply these tools to rectify defects and issues emerging during the production processes. SPC charts and other basic quality tools are commonly applied to understand and explore process anomalies in the supply chains. Moreover, review of studies finds that fashion and textile firms are good at applying quality control systems such as ISO 9000 standard along with common SPC tools. However, SMEs are lacking its appreciation in their supply chain processes.
Trainer 2012
A study from Hill et al. 2018 on the implementation of Six Sigma in MRO maintenance, repair and operations case found that common issues on the project were feedback from employees, commitment of the operational staff, and lack of strong leadership drive to push project forward. During the implementation, the study found the people with expertise at operation were away to manage operational and supply chain tasks. Furthermore, continuous training, development of staff and effective communication throughout the project is essential to Six Sigma as part of quality management programs. Hill et al.
2018 4 Ergonomic Concept and Tool 4.1 Overview
Ergonomics is defined by the International Ergonomics Association (IEA) as the scientific discipline concerned with the understanding of interactions among humans and other elements of a system, and the profession that applies theory, principles, data, and methods to design in order to optimize human well-being and overall system performance. IEA 2021. It takes account of physical, social, technical, cognitive, organizational and environmental aspects when humans interact with systems which include other humans, processes, tools.
Machines and Technology
The goal of ergonomics is very much related to the Murray concept of lean manufacturing, that means avoiding physical strain, bending to work, lifting heavy weights, repeating tiring action or overwork.
Denning, Ares et al. 2015
Additionally, Murray concept includes elimination of wastes not only related to physical burden but also related to mental burden, particularly addressing the motivation and welfare issues of the workers,
G.
workers' autonomy, participation and engagement. Areses et al.
2015 Eswaramoti et al. 2010
As such, ergonomics and lean manufacturing are complementary to each other.
4.2 Ergonomic in Lean Management
There is evidence that ergonomics is integrated in the lean manufacturing approaches. For example, an ergonomic risk assessment tool was incorporated in the original Toyota car assembly lines, which is called Toyota Verification of Assembly Line, Benders and Morita 2004. In this tool, ergonomics risk factors,
G.
physical workload and demanding tasks were identified, and solutions were developed by the assembly workers themselves using Kaizen continuous improvement techniques. Solutions developed included the comfort car seat, where the worker was seated in a location in the car with close reach of the assembly locations without difficult physical body extensions. This intervention reduced musculoskeletal discomfort, increased productivity, and improved quality. Another example is a study of 41 lean manufacturing projects in various industries, including textile, in Portugal. Alves et al.
2019
Like the Toyota Verification of Assembly Line, another assessment tool,
E. The Ergonomic Workplace Assessment, EWA, Ahonen et al.
1989, was used to identify the ergonomics risk factors. Out of 14 ergonomics risk factors in the EP.5 addressed 10 risk factors, standard work 9 risk factors, visual management 6 risk factors, SMED, single minute exchange of die, 6 risk factors.
And Poka Yogurt for Risk Factor.
These 5 lean manufacturing approaches covered 13 out of 14 ergonomics risk factors such as worksite, general physical activities, lifting tasks, postures and movements, accident risks, job content, job restrictiveness, communication and personal contacts, decision-making, work repetitiveness, attention, lighting conditions, and thermal conditions. Only noise risk factor was not addressed, possibly because there was no workplace that has elevated level of noise. 4.3 Ergonomics tools in fashion and textile industry. Ergonomics is particularly important because fashion and textile industry is labor-intensive that may require intensive manual handling, thus, leading to poor body posture and repetitive movements. There are several studies that validated the effectiveness of ergonomics integrated with lean manufacturing in terms of improvement of quality and well-being of workers in textile industry. For example, Veve and Erdinch 2008 and Erdinch and Veve 2008 introduced quality improvement through ergonomics quite methodology in a textile factory in Turkey, which integrated the Kaizen's continuous improvement approach and an ergonomics assessment tool. The tool identified the main cause of 36 sewing operators' poor quality performance, i.e., poor postures due to bending of neck and body during the monitoring of machine stitching operation. Ergonomics intervention of correcting the posture, i.e., by tilting the single needle straight stitch Makindi 4.2 degrees. This has resulted in reduction of defects from 7% to 3.4%, Erdinch and Yao 2011. There are other researchers who integrated ergonomics and lean manufacturing in other labor-intensive industry. For example, Axelson 2000 introduced Select, Interpret, Measure, Progress, Learn and Echo simple methodology in an assembly plant in Sweden. It is a combination of Kaizen's continuous improvement, QC tools particularly the Pareto principle and an ergonomics assessment tool. Through the tool, it was discovered that the 17 out of 40 tasks with poor body postures contributed 70% of the plant's quality problems. Ergonomics interventions such as improving work body postures, lighting conditions, accessibility of materials and the comfort of assembly procedures have reduced the rejection rate from
9% to 5% and
improved the well-being of the workers. This section introduces some ergonomics assessment tools that can be incorporated in lean manufacturing approach in textile industry, i.e., the tools that evaluate ergonomics risk factors.
Chayasan et al.
2012 has identified 8 popular tools, i.e.,
the Quick Exposure Check QEC, Finnish Institute of Occupational Health EWA, Job Strain Index, JSI, Hand Activity Level, HL, the Occupational Repetitive Action, OCRA, Index.
the Rapid Upper Limb
Assessment Method, RULA, the Rapid Antibody Assessment Method, REBA, and European Standard for Safety in Human Physical Performance, EN 1005-3.
Below is a brief description of the tools together with their strengths and weaknesses.
The QEC, David et al.
2008 measures musculoskeletal disorder, MSD, factor at the neck, back, arms, upper extremities, and overall body. It takes into consideration of movement frequency, force applied, posture, and duration.
The EWA, Ahon et al.
1989 has 14 areas, i.e., physical workload, workstation design, lifting, accident risk, working posture and movements, multiple body areas. Task restrictions, task content, decision-making, personal contact and communication, repetitiveness, attention required, noise, thermal environment, and lighting. Both the QEC and the EVA are particularly useful tools for initial ergonomics assessment because they can be easily learnt and can be conducted quickly, Chasson et al.
2012.
The worker's perception is included, which can be both an advantage and a disadvantage. Workers know best about the problems they face in their workplace and their discomfort and difficulty in body movements. However, their opinion may be biased because of the searchlight effect, i.e., they know they are being observed. Thus, they might try to provide polite answers rather than the truth of the actual situation. JSI, Moore and Garg 1995, and HAL, American Conference of Governmental Industrial Hygienists 2002, measure the MSD risks at the hands and wrists. Both tools require a time motion study, and they are suitable for evaluation of workstations with short cycle time, Chasson et al.
2012.
They consider the perceived exertion and its duration within the overall cycle time. Additionally, they consider the worker's perception. However, both tools have a different measurement for repetitive movement, Chasson et al.
2012.
The OCRA, Columbini 1998, measures MSD risk factors, particularly repetitive movements at the shoulders, arms, wrists, and elbows. Like JSI and HAL methods, it considers the risk of exposure within the overall cycle time. The OCRA and the QEC have more than 70% agreement when evaluating workstations with high-risk level, Chason et al.
2012
The OCRA covers many work characteristics. However, it takes 2.6 times longer to complete an assessment compared to using the QEC toolthis. It is costly to use, particularly for large sample size, Chason et al.
2012
The rule at McAdamney and Nigel-Corlett 1993 measures MSD risk factor at the upper limbs, which includes the shoulders, upper and lower arms, wrists, trunk, and neck. It takes into consideration the posture, load and repetition movement. The Reba, Hignett and McAdamney 2000 measures MSD risk factor at the entire body, including legs, trunk, neck, shoulders, arms and wrists. It also has the final score like the RULA. Both tools have a final score that determines if an ergonomics improvement is required. They are easy to learn and use and can be performed quickly.
based on ชยสัน et al.
2012, they take about the same time to complete. However, both tools take a cross-sectional assessment of a work cycle, thus, they may not represent the whole cycle. Liu and Yao 2015 recommended the observation of several cycles through video recording to determine the work case scenario e.
G.
The worst postures when recording the scores. The RULA and the Reba have high agreement with the QEC tool.
according to ชยสัน et al.
2012, more than 90% workstations identified as high risk by the QEC tool were also identified the two tools. Lastly, N1005-3 tool measures the acceptable force applied during a work. For example, it stipulates the maximum acceptable force applied to the shoulder joint based on the 15th percentile of workers. The acceptable force also takes into account of the duration, frequency and speed of the action performed. Like OCRA method, it considers many work characteristics. However, it is costly to use as it takes much time and difficult to learn.
Both OCRA and EN 1005-3 are not suitable for preliminary screening study, ชยสัน et al.
2012, most of the above assessment tools make use of observational methods.
I.e.
The assessor observes the work performed and estimate the measures e.
G. Posture, angle, load, repetition, and bending.
On various body locations such as upper limbs and lower limbs, based on a set of standards. Scores are assigned according to the standards and then calculations can be done to get the final scores e.
G.
The RULA and the Reba. Based on the scores, the risk factors for specific body locations are identified. For those with high scores, which indicate high risk, ergonomics improvements will be conducted through redesigning of workstation, work process and tool. The purpose is to reduce or remove the risk factors. After the improvements, the assessment tool will be used again to validate their effectiveness in removing the ergonomics risk factors. One example of the use of tools is the application of the RULA in brazing operations of air handler production, Liu and Yao 2015. The RULA was used to identify the arm, wrist, neck and posture risk factors in the brazing task. The tool identified a final high-risk score
E.
7 which required urgency to investigate and make changes to remove the risk factors. The tool identified bending of neck, raising of arms, twisting of wrist and bending of back during the brazing task throughout an 8-hour shift. The workstation was redesigned by raising it to avoid bending of back. The single brazing gun was modified into a twin brazing torch so as to avoid the need of twisting the wrist and bending of neck when the operator works the flames around the joint area. This movement was replaced with straight line movement perpendicular to the joint area with use of the twin brazing torch. After the ergonomics improvements, RULA was used again, which resulted to a lower final score of 3. The results also improved quality by 59%, increased productivity by 140%, reduced waste of filler material, silver alloy, significantly and saved $79,000 USD per year. Additionally, it improved the well-being of the workers through the reduction in pain in the neck, shoulders, wrist, and lower back. In conclusion, this section explains what ergonomics is, why and how ergonomics can be integrated with lean manufacturing through the similarity in their goals. Justification was also given of the importance of ergonomics in fashion and textile industry,
E.
Its labor-intensive nature and evidence of ergonomics integrated with lean manufacturing through Quite methodology, Erdinchen Yao 2011, together with the effectiveness in reducing quality defects and improving workers' well-being. 8 ergonomics assessment tools were introduced and discussed in terms of their strengths and weaknesses. Lastly, an example of application a tool was given together with its effectiveness. The limitation is this section only focuses on the most common ergonomics tools that are useful for lean manufacturing in fashion and textile industries. There are many other ergonomics tools, methods, and techniques that can be used in lean manufacturing. For example, the mathematical modeling of ergonomics in hybrid assembly lines for safe assembly.
Work Motti et al.
2017, and integration of multiple ergonomics assessment tools and questionnaires, ergonomics improvement methods in the context of human-robot collaborations, Column et al.
2021
However, due to the constraint of space, and their limited use in fashion and textile industry, they have been excluded from this Chapter 5 conclusion. Fashion and textile manufacturing processes are often quite inefficient, due to multiple complex stages, labor-intensive work and high changing demand. As the industry gets more competitive, fashion and textile firms are under pressure to optimize production, achieve better forecasting accuracy, reducing product defects and increasing work safety. The key challenges in achieving competitive textile manufacturing practice are to identify sources of wastes, reduce product defects and reduce injury-prone activities due to its highly manual and
intensive work nature.
The chapter introduces 3 lean manufacturing approaches as solutions to cost reduction and resource optimization in the fashion and textile manufacturing.
First approach, MILDA, A waste identification technique, identify 7 waste element in any established supply chain, Chama 2013, Vanesek et al. 2018.
These wastes once clearly recognized can help firms to eliminate inefficiency, reducing defects or prioritize resources on most productive activities. Second and third approaches including statistical process control and Six Sigma, respectively being part of the TQM suite, focus on monitoring and identifying process variations from a baseline model. In manufacturing and supply chain process performance, Niastani 2017, which can help understand the nature of the mistakes during the production process, Tuna 2018. Another key issue of the fashion and textile manufacturing is work safety or ergonomics due to its intensive manual labor, poor body postures and repetitive movements of the workers. The chapter introduces 8 ergonomics assessment tools that can be incorporated in lean manufacturing in fashion and textile manufacturing to evaluate ergonomics risk factors. The main objectives of applying ergonomics integrated with lean manufacturing are to reduce quality defects and improve workers' well-being. It was established through the case studies that the fashion and textile industries can be benefited by applying the lean manufacturing approaches and the ergonomic tools.
Reference, Ahonen M, Lonis M, Kuoringa T, 1.
This chapter aims to highlight the digital technologies that are designed to complement the operation of lean manufacturing. Firstly, Industry 4.0 has been explained that helps to complement lean manufacturing to gain continuous improvement, better customer satisfaction and improved operational efficiency. The results of combining digital technologies with lean manufacturing yield the concept of Lean Industry 4.0. Secondly, blockchain occurs as a disruptive innovation to resolve the problems of lack of an integrated lean management system across the supply chain network, which is also discussed. Thirdly, the radio frequency identification (RFID) system is analyzed, and its ability to offer high levels of accurate, real-time information, decrease time-consuming activities and labor cost while increasing product visibility and operational speed is covered. Fourthly, artificial intelligence (AI) and robotics are also discussed with the ability to deal with complexity, increase productivity and efficiency with the automatic system, and decrease production
cost.
Finally, Other non-common yet useful tools are mentioned to give a comprehensive view of the application of digital technologies with lean manufacturing, including automated guided vehicles (AGVs),
V
tool stimulation (VS), and cybersecurity. To consolidate our findings, two case studies are presented to give realistic viewpoints of digital technology adoption from two giant firms in the textile and apparel industry, namely Uniqlo and H&M. The findings of a survey based in Vietnam's fashion and textile industries on the use of technology such as RFID is also included in this chapter.
Keywords Industry 4.0 Blockchain Find Artificial Intelligence Robotics Automated Guide Vehicle 1. Introduction.
Ever since the first industrial revolution, the manufacturing sector has always been changing and improving compared to its original version. What causes those changes are undoubtedly various technologies.
Sander et al.
2016 noted that, with the same purpose of making the production process more efficient, while the Western companies choose to apply advanced technologies such as automation or computational technology into the process to make it more streamlined, the world has witnessed another capable manufacturing principle called lean manufacturing derived from Japan with the huge success from the Toyota Motor Corporation, Chiarini et al.
2018
With those two methods being the fulcrum, automation and lean manufacturing, companies and industries around the world have attempted to apply either one or both approaches to achieve competitive advantage in the more intense competitive markets in today. In light of the fourth industrial revolution, the concept of lean manufacturing, although still maintaining its core objective of enhancing processes productivity by simultaneous methodologies including waste elimination, product quality improvement, lead time reduction and cost contraction, Fullerton et al. 2014, the approaches towards achieving those goals are evolved to some extent. The reasons behind this shift can be explained by the new production stand in this Industry 4.0 era, Valamed et al.
2020
Particularly, Industry 4.0, some may refer to the term smart manufacturing, requires new ways for production in response to the strong rise of smart digital technologies. Thus, the existing physical manufacturing production and business operation can be now developed to a new level to be smarter and connected with the integration of technology.
Data and Network Application According to Varela et al.
2019, the new age of production considers lean manufacturing and Industry 4.0 as the modern fundamental pillars for companies to attain business productivity and sustainability. The effectiveness of using advanced digital technologies to reinforce and accrete lean manufacturing should be put into more investigations for drawing a final conclusion. However, this chapter will introduce and demonstrate some of the promising technologies that can be applied in firms to improve their manufacturing performance, thus aligning with the objectives of lean
Manufacturing.
This chapter has discussed the application of various digital technologies such as Industry 4.0, blockchain, RFID, AI and robotics in lean manufacturing. These digital technologies are designed to complement the operation of lean manufacturing for improving the effectiveness to achieve the objectives of lean. Furthermore, this chapter includes the findings of the research work on the implementation of RFID in the fashion and textile manufacturing industries in Vietnam, the third largest global clothing
Porter, Nayak et al. 2019
Due to significant role of Vietnam in global fashion and textile industries, we conducted a survey on a total of 11 Vietnamese fashion and textile enterprises. A qualitative interview was done on the status of implementation of RFID technology in fashion and textile industries, and the views expressed by the manufacturers have also been included. This qualitative research will help to improve the understanding of the readers on the implementation of technology in real-life conditions.
2. Digital Technology for Lean Manufacturing 2.1 Industry 4.0
2.1.1 The evolution of Industry 4.0. The manufacturing sector has passed through 4 stages of evolution, from Industrial 1.0 to 4.0, that also come along with the transformation of nearly all facets of manufacturing, including changes in the way products are produced, consumer expectations, and especially how firms improve their productivity to adapt or innovate in the changing of competition landscape. Fujimoto 2012. A brief summary of the 4 industrial revolutions is discussed below and listed in Table 1. Table 1 Brief history of the 4 industrial revolutions.
Industry Period Energy Resource
Main technical achievement. Main developed industries.
Transport mean 1.0 1760 ถึง 1900 Coal Steam Engine Textile Steel Train 2.0 1901ถึง 1960 Oil Electricity Internal Combustion Engine Metallurgy Auto Machine Building Train Car 3.0 1961ถึง 2000 Nuclear Energy Natural Gas Computer Robot Auto Chemistry Car Plane 4.0 2001 Present Green Energy Internet 3D Printer Genetic Engineering
High-tech industries.
Electric Car Ultra Fast Train Reproduced from Prisca-Group 2016
In 1760, along with the invention of the steam engine and hydropower, the first industrial revolution happened that indicated the huge development in the way products are created. In fact, the steam engine worked like a milestone that transformed the economy from mainly agricultural and farming-based into a manufacturing epoch. Also, in this phase of manufacturing, coal was used as the main energy source, helping two industries, textile and steel, to become dominant and among the largest sectors for economic growth. In the 1901, the second industrial revolution started, which is being highlighted with the discovery of the internal combustion engine. Taking this as the base, widespread industrialization occurred with the introduction of more modern production lines such as the automatic assembly lines and, more importantly, the mass production that came along with the usage of electricity. Around the 1961s, the third industrial revolution began, and the focal point of this stage was the rise of electronics, information technology, specifically telecommunications and computer systems. The third industrial revolution worked as a very solid cornerstone for the fourth industrial revolution, Prisca-Group 2016. Officially named in 2011, as the Industry 4.0 started with a fine amalgamation between physical and digital aspects with the crucial involvement of advanced technologies. Gobeklu 2020.
Exter et al.
2018 asserted in their research that the unique characteristics of the Industry 4.0 in comparison to its predecessor belong to the superiority of technologies, greater velocity and impact of Informa-Tion systems on the process. At the moment, when the fourth industrial revolution comes into the picture, its intense impact on human productivity cannot be neglected, especially when talking about the significance of its facilita-Tion on the speed and efficiency that could be achieved. Lee et al.
2182
1.2 What is Industry 4.0? Coming at the dawn of the 21st century, Industry 4.0 is all about adopting advanced digital technologies to improve production, intercommunication and data-driven decision-making processes.
Nen, Lee by Gathering Real-Time Data for Analysis, Wang et al. 2016
Those technologies' devices will interconnect to each other, creating a seamless sequence of communicating, analyzing and performing, thus boosting the efficiency of operating tasks.
According to Hageem et al.
2020, traditional manufacturing can now be turned into a more smart and autonomous process using the Industry 4.0. The key driver, as indicated above, relies on the interconnectivity between the horizontal and vertical spheres consisting of materials, machinery and operators. As a result, a networked smart manufacturing system is created. 2.1.3 The aim of Industry 4.0. As stated above, with digitalization being the trait of Industry 4.0, it is possible to create a more than ever interrelationship between everything and everyone in a system, including processes of logistics, production, capital and human resources, hence, making across technology and linking every element within and without industries together.
Fragapan et al.
2020 found that by adding the real-world virtual components, Industry 4.0 aims to enhance flexibility, responsiveness, intelligence, and most importantly, the overall efficiency of the manufacturing process through the improvement in data analysis and data transferring.
Hageem et al.
2020 claimed that Industry 4.0 makes the process become smarter and more automatic by replacing traditional practices with computerization. Apparently, the higher level of interconnection and automation brings better unification in the production process. A more collaborative operational method could be generated with technology-driven supports. Thus, A higher operational productivity and efficiency could be achieved in manufacturing process, Alcácer and Cruz Machado 2019. Taking Industry 4.0 as a foundation, firms are expected to upgrade their manufacturing process into a whole new standard, where smart manufacturing and smart products are incorporated. Industry 4.0 is considered as the promising technology for innovating the whole manufacturing industry, in which continual data stream and effective communication will drive into more efficiency in UT.
Leasing Resources นยัก2020
2.1.4 Industry 4.0 Tools. At the moment, there has not been an agreed upon list of technologies that best represent the application of Industry 4.0. The list of noted technologies varies in different research papers.
According to Turk et al.
2019, the differences on the concept of digitization in different countries may be related to how Industry 4.0 performs in the country. Some featured technologies for Industry 4.0 are Internet of Things IoT, cloud computing and big data analytics, which can be used to generate a computational physical system, LU 2017. There are supplementary systems used to support the aforementioned technologies, namely robotics, artificial intelligence AI, 3D printing, additive manufacturing, and automatic vehicles.
According to Alcácer and Cruz Machado 2019, Industry 4.0 is an inclusion of 9 fundamental technology.
This framework is believed to be sufficient for creating a well-rounded integration in both horizontal and vertical directions for an end-to-end engineering synthesis as well as a typical network DEM.
And Manufacturing System Akinlabi 2020.
Thus, when effectively integrating those technologies, an advanced manufacturing system is achieved, called Cyber-Physical System (CPS). Becoming even smarter, factories are bringing automation to be the main function in a production process that can now make decisions and execute tasks beyond human controls, Azuz and Pierreval 2019.
Grassler and Yang 2016.
All the mentioned tools used in Industry 4.0 are summarized in Fig.
1 Fig.
1. The main tools of Industry 4.0. The above framework is also aligned with the findings from Campbell et al.
2020. Although the above framework Fig.
1 is not separating Industry 4.0 technologies into primary and supplementary types. These technologies are vital for the operation of Industry 4.0. The list of Industry 4.0 technologies based in the
Application domain has also been given in Table 2. Table 2 Key Technology representing Industry 4.0. Purpose Industry 4.0 Technology.
Smart data collection, storage, analysis, and sharing technologies. Big data analytics BDA, cloud computing CC, Internet of Things IoT, and sensors, simulation, and prototyping.
Top floor technology.
Additive manufacturing AM, virtual reality VR, augmented reality AR IoT, sensors, and robotic systems RS.
Integration technology. Cyber Physical System CPS and Cyber Security System CSS. Reproduced from Campbell et al. 2020.
2.1.5 How Industry 4.0 Helps Lean Manufacturing. In accordance with De Merkel and Al Futea 2020, when investigating the relationship between Industry 4.0 and lean manufacturing, it can be said that Industry 4.0 works as an applicable set of tools to support lean manufacturing. When considering the purpose of lean manufacturing, waste reduction and continuous production flow appears as the two most important principles, Thangaraju and Smith 2015. To reach the optimal performance in lean manufacturing, it is necessary to resolve 7 categories of wastes, as listed here.
Defect, excessive inventory, transportation, overproduction waiting time, overprocessing, movement.
In fact, there are many well-designed tools used to address the goal of lean manufacturing such as Kaizen principles, just-in-time JIT, production, Six Sigma and 5S, which are discussed in other chapters
of this book.
Although these tools are more likely to be presented as theoretical methods and frameworks, how manufacturers implement the tools in terms of physical and mechanical execution still depends on certain
situation.
Therefore, when Industry 4.0 comes with a variety of digital technologies, it also brings up a more straightforward solution to attain lean manufacturing. More specifically, when the goals of the two concepts, achieving production efficiency and higher resource utilization are considered. Industry 4.0 application can certainly support to achieve the
Goal of Lean Manufacturing Wagner et al. 2017
There are fundamental differences when carefully comparing the two concepts, Industry 4.0 and lean manufacturing. One significant difference that must be put into deliberation is that while lean manufacturing involves people's inclusiveness, Industry 4.0 tends to center on the role of computer-based and automation.
System
In lean manufacturing, the harmony in people's interaction with each other and with the production system is essential, and people are always put at the core focus in the process. Gallardelli et al.
2019
In contrast, Industry 4.0 concentrates more on the function of technology with computer-based systems and automation.
According to Tauber et al.
2017, the ultimate goal of Industry 4.0 is to create smart manufacturing systems, whereas the goal of lean manufacturing is improve the productivity by eliminating unnecessary waste. Additionally, in Industry 4.0, the significant role of data either in data transmission or data-driven decision-making is appreciated at a much higher level than in lean manufacturing. Thus, the utilization of big data is considered as one of the key pillars in building networked systems. Overall, the philosophies of lean manufacturing and Industry 4.0 can impeccably complement one another. In a nutshell, Industry 4.0 helps in gaining continuous improvement with the application of digital technologies for better addressing customer expectations and facilitating higher level of efficiency
and productivity.
In the era of Industry 4.0, a new notion could be generated, sustaining with the quintessence of both concepts, called Lean Industry 4.0 Inches Esmont et al.
2020 2.2 Blockchain
2.2.1 What is blockchain? According to Christidis and Devitsikiadis 2016, blockchain is a distributed system to cryptographically capture and record a consistent and direct chain of transactions between individuals within the
same network.
When a transaction is completed, a new block is formed under the format of a data package to record the information related to the transaction. The verification of each block follows governance rules in the blockchain network. Wang et al.
2019
Each block after being created is linked together in an irreversible chain to block the transaction. Nofer et al.
2017
This means that after creation, any block in the system blockchain cannot be deleted or adjusted by any participants, which explains the choice of terminology blockchain. In summary, a blockchain includes multiple data sets which are created by a chain of blocks that possesses information of a transaction. Goad et al.
2020
Furthermore, each block has not only the information of the transaction but also a timestamp, a hash value of the prior block, parent block, and a nonce
e.
a random number to verify the hash. With the association between the blocks, having the hash value of the parent block and the nonce can ascertain the integrity of the whole chain to the very first block, genesis block. Moreover, since hash values are idiosyncratic, they will change accordingly to any attempts to change the block, and consequently, this will notify the system since the hash values are no longer matched. Hence an effective function to detect fraud. Nofer et al.
2017
Nonetheless, it is not true that all transactions are automatically added to the block strings, which are included in a ledger. Instead, each transaction must go through a consensus mechanism of validity of transactions, which requires the agreement of the majority of blocks in the network, and the validity of the pending block, to be supplemented in the string. Nofer et al.
2017
Swanson 2015 mentioned that consensus mechanism is a framework that a majority of network validators agree on the rules and procedures set by the ledger, which enables archiving coherent set of facts between participating blocks in the network. It means that instead of being added directly to the chain, this process warrants that the transaction is fully stored in a block for a certain time before being transferred to the ledger. 2.2.2 Characteristics of blockchain. Blockchain is a type of database architecture created with the distributed ledger technology as a foundation.
Schmidt and Wagner 2019
Therefore, unlike traditional database networks, it has some key characteristics such as open distributed ledger for public verification. Blockchain is designed as a decentralized system, therefore, it is distributed and shares the copies of all information to all the participants within
the network.
Equivalently, This can be understood that blockchain is not under control of specific third-party intermediaries such as governments and banks.
Hence,
information can be updated faster by the participants within the network as the new block will be created and linked to the previous block to update the information of the transaction without the need for centralized authority, hence limiting costs and time. Moreover, with the real-time updating of information, blockchain is a useful tool to adopt when involving different parties and transactions. Corpella et al.
2017
Transparency. The transparency of data and the updating process is a required element for public verifiability. Every transaction is transparent and visible across the network regardless of the need to access all information of the participants in the network. Vust and Gervais 2018. Cryptographically sealed and immutability of data. One of the utmost important pillars of blockchain is cryptography. It is needed for digital signatures and data integrity to avoid manipulating blocks after the transaction has been validated and recorded into the blockchain database. This cryptographic mechanism creates the immutability for data stored in blockchain because it cryptographically connects all new blocks to the parent block.
Woods and Gervais 2018
Consensus mechanism and trustiness. As mentioned above, before being officially added to the blockchain, transaction must be stored in the block and meet the agreement of majority validators using consensus protocols, including proof of work (POW), proof of stake (POS), and the proof of elapsed time (POET). McQuinn and Castro 2019. This mechanism can hinder the risk of wrong inputs and fraudulent conducts that could impact the database network.
2.2.3 Blockchain 1.0, 2.0, and 3.0
According to Swan 2015, the current activities and potentials of the blockchain revolution can be classified under three categories. Blockchain 1.0, digital currency. Blockchain is used as cash in the form of digital currency. Furthermore, it can function normally with basic features as currency remittance, transfer, and digital payment.
Blockchain 2.0 Smart Contract
Blockchain is further employed in the market and financial applications for transactions that are more extensive than cash, including stocks, bonds, loans, futures, mortgages, titles, smart property.
and Smart Contract Blockchain 3.0 The Future
The potential application of blockchain beyond currency, finance, and markets, including the application in logistics and supply chain. 2.2.4 Application of blockchain on lean manufacturing. Lean manufacturing, created by the Toyota Motor Company in the middle 1970s, aims to minimize waste and non-value-added elements within the production process, such as unnecessary space, non-value added steps, prolonged lead time, excessive inventory, defects, and overproduction. Bozarth et al.
2008
Lean management system is an extension of lean philosophy from a single plant to the entire supply chain network. Holweg 2007.
According to Liu et al.
2013a. B. It is unlikely to have an integrated lean management system across the network due to the differences in preferences and priorities of the decision makers at each stage of the supply chain. Furthermore, from the perspective of Schmidt and Wagner 2019, lean practices in supply chain networks inevitably cope with various types of risks stemmed from the relationship between suppliers and buyers, namely opportunistic behavior, negotiating power imbalances, and asymmetry information. Hence, a systematic database is believed to be the solution to this alerting matter. And blockchain is full of potential to perform a solution that can integrate lean practices to the whole supply chain. Network is discussed below. Firstly, supply chain is normally visualized as a complex network of systems with multiplex logistics, a wide range of data, and their relationships. Therefore, minor errors can lead to the bullwhip effect, causing massive delays. Harnshaw and Wilson 2013, Lee et al.
1997
Nonetheless, blockchain is a digital ledger with available access by all the participants within the network. Real-time updating features can enable transactions, records, and processes to be observable across the entire supply chain network. Hence, it is easier for stakeholders to monitor and detect problems
in real time.
Furthermore, since blockchain allows data to be synchronized and shared throughout the network, it saves cost by eliminating unnecessary steps and time that is normally caused by document duplication in the traditional process.
Lawrence 2019
Secondly, blockchain is capable of being a digital platform to implement smart contracts. which are self-validating and self-executing agreements between parties in the supply chain network once certain.
Condition are met โดยกี่ et al. 2020
According to Mint 2019, these smart contracts enable entities in the supply chain network to exchange shares, money, or even property in a transparent way by eliminating the third-party intermediaries. Ultimately, smart contracts help corporations to benefit from lower transaction costs with the cutoff of intermediaries during the process and facilitate order fulfillment by minimizing delays between delivery and payment. Thirdly, blockchain can ensure and enhance trust between all stakeholders in the supply chain network, including suppliers, buyers, and focal firms. This is concluded based on the immutability of data feature, since every new transaction after being added to the blockchain will be cryptographically sealed and unable to make changes. Vust and Gervais.
2018 Furthermore, Saberi et al.
2019 added that the tamper-evident nature of blockchain can diminish the opportunity costs that often exist among stakeholders in the supply chain network. From the above discussions, it can be concluded that blockchain will be working as an important technology to achieve the objectives of lean manufacturing.
2.3 RFID Technology
2.3.1 Introduction to RFID Radio Frequency Identification. RFID refers to the process of exchanging information between stationary and mobile units using radio communication, LAN 2005.
which is becoming an indispensable part of our daily life.
Through a thick array of data, information regarding the location and entity of properties can easily be traced through wireless scans, which is further applied to imaging, localization,
Sensing and Security 2015
RFID technology is becoming more popular due to the increased integration with Internet of Things, machine-to-machine M2M, and ambient intelligence, offering a faster, yet lower-cost, structural simplicity and less power consumption demanded for the tag circuits. 2.3.2 History of RFID. RFID technology started its journey from World War II, when radar was discovered by Sir Robert Alexander Watson, a Scottish physicist, in 1935. This radar was used to alert approaching aircrafts, identify whether they are from the Allies or enemies, and inform the Army, also known as an Identify Friend or Foe (IFF) approach. The technology was then widely utilized, in which certain innovations were recorded in Germany. The radar could alter its reaction signals, convert them to be more translatable. The British also took advantage of this technology, in which radar played as a trustful transmitter from the ground to detect friendly aircrafts for planes. From 1950s to 1960s, the existence of various scientific articles proved the effectiveness of RF range in identifying objects remotely. Radar and RF systems were then further developed by the USA and Europe researchers. The first exploration of RFID technology was started by Harry Stockman in 1948, when specific reflected power communication problem was solved. The concept embedded in RFID technology remained as a secret between 1960s and 1970s. Later, the technology continued to be developed into a tracking system for nuclear and sensitive materials by the Los Alamos National Laboratory in the USA. The advantages of the technology were then exploited by investors, educational centers, programmers, and government laboratories. In January 1973, an U.S. patent on active RFID tag was received by Mario W. Cardullo, allowing memory to be rewritten. The technological developments were reported to be more sophisticated in manufacturing in between 1980s and 1990s, while the RFID system succeeded in scanning up to millions tags in the USA automotive
sector.
In 1999, an Auto ID Center, specializing in automatic identification, was established by the Massachusetts Institute of Technology (MIT) and received enhancements from the Uniform Code Council
Procter
and Gamble, Gilly and Ian International. With significant development of the RFID technology, Auto ID Center was supported by over 100 corporations, including the U.S. Department of Defense and other key RFID vendors during 1999 to 2003. Its research laboratories were then distributed to the UK, Australia, Switzerland, China and Japan, with the establishment of two air interface protocols, while marking its evolution to the electronic product code EPC to promote the EPC standard. The EPC Global, with its RFID technology, soon stood at the second standard to receive the most utilization from many industries. While environmental issues were becoming top concerns, 2010 marked a considerable achievement with decreased cost of tags and increased performance to reach a sustainable standard of the RFID systems. At present, the RFID technology is evolving from the security technology to serve the Army, to various industries including health, lifestyle, automotive, logistics, transport, aerospace and fashion. This system was also certified by the International Organization for Standardization (ISO) for a high-leveled interchangeability of a technical standard. The RFID varies in frequency bands, from a microwave level 2.4-2.5 GHz to the recent development of the UHF ultra-high frequency Generation 2 869-969 MHz CHU 2015. The RFID, an application from a wide range of expertise Weinstein 2005, has been through a long history Table 3 and is continuing its sustainable development that adapts current requirements of BUSI.
Needs and Society
Table 3 The history of RFID technology.
Time Frame Event World War II 1935
Radar was discovered and used as an identify friend or foe IFF approach.
1950s-1960s
Radar in RF ranges effectiveness was being proved. 1948. Harry Stockman explored RFID by acknowledging certain reflected power communications problems had been solved. Domduzisa et al.
2017 1960s-1970s
RFID was utilized as the tracking system for nuclear and sensitive materials for Los Alamos National Laboratory in the USA.
January 1973 Mario W.
Cardullo acknowledged the allowance for memory to be recorded by the U.S. Patent Active RFID tag.
1980s-1990s
The system became more sophisticated, managing to scan millions of tags in the USA automotive sector. 1999. MIT founded Auto ID Center, specializing in automatic identification. 1999-2003. Auto ID Center received supports from over 100 corporations, U.S. Department of Defense and RFID vendors.
October 2003
The Auto ID Center was changed into EPC Global, with widespread distribution around the world.
December 2004
The system became the second technology suppliers for many industries.
2010s
The application of RFID marked considerable decreased cost of equipment and tags and increase in sustainable performance. The technology is applied in a diversity of industries. 2.3.3 Functions of RFID. The functions of RFID are illustrated as in Fig. 2, in which information is delivered through an RFID tag, antenna, reader and controller CPU central processing unit. Particularly, when the information is required from an RFID tag, a signal will be delivered by the CPU to the reader. Through the antenna, the reader will transfer the digital information back to the CPU from the RFID tag Fig. 2 Functions of RFID systems. This process is supported by a structural network of wired and wireless communication infrastructure, in which the reader will sense the radio signals and broadcast it to the antenna of the tag. When receiving the signals, the data can be read from the chip via radio wave, and with this done, the reader can simultaneously and accurately process and store data from a large number of tags. This process is considered to be more sustainable in comparison to the current barcode systems allowing only single tags scanned per time.
Fenani et al.
2011 proposed three main components of the complicated digital RFID system. This includes the RFID tag, RFID reader and RFID controller.
RFID tag
The RFID tag, known as the transponder, is a small device made from a silicon microchip in the antenna. Chechi et al.
2012
In a simpler word, RFID tag is actually a tag that can be found on any selling items or boxes. The data in the RFID tag can be delivered wirelessly through a chip with different power requirements. Hence, RFID tag is classified in different aspects as shown in Table 4. Table 4 RFID tags classification. Classification of RFID tags.
Passive tag
With the passive RFID tag, the electromagnetic signal is transmitted forward and backward from the reader with integrated circuit power, Fenini et al.
2011
This type has limited energy, hence, restricts the distance between the reader and tags as well as the capacity of circuit power in the computer. With such limitations, passive tag is usually cheaper than the other types.
Semi-passive tag
In the semi-passive tag, the battery is the power source for the integrated circuit to achieve a more special processing journey but still with the passive transmission module. This is considered an advanced type from the passive tag, despite such restrictions from the waiting time that create unacceptable delivery time from dormant to active state. Morose 2004.
Active tag
The last and also the most powerful type, comprising better and larger capacity from the passive tag, with further and wider distance allowed to transmit data between tags and the readers, which can vary due to the transmission frequency. Above all, the active tag can be incorporated with a sensor with complicated circuits embedded inside, allowing the system to operate advanced features during its operation. The price of an active tag can reach up to $100. Memory type of RFID tag.
Read-only tag
In the read-only tag, the memory has already been programmed in the factory. Hence, the static data cannot be changed after the manufacturing process. This tag also is limited in space to store the data, so the price is cheaper.
Read-write tag
The concept of storing data is the same as the read-only tag, except that the read-write tag provides a more flexible way to process the data. Through the usage of this tag, data can be easily altered. Wireless signal type between the tag and the reader.
Induction method
The induction method utilizes the LF and HF frequency bands for close proximity electromagnetic or inductive coupling near fields. Chechi et al.
2012 Propagation method
The propagation method, however, utilizes the UHF and microwave frequency bands for propagating far-field electromagnetic waves. Chechi et al.
2012
An important part of the RFID tag includes the RFID antenna. This device is known as the data storage unit for any tag, varying in types from patch, linear polarized, stick, adaptive, gate and omnidirectional antennas. To perfectly perform, RFID antennas should fulfill the following criteria.
1. It should be in an acceptable and omnidirectional or hemispherical coverage. 3.
It should deliver signals to the microchip at the highest rate.
4.
It should perform robustly.
5.
It should be cheap to adapt to the RFID systems.
เครื่องหมายสงวนลิขสิทธิ์ The Author S Under Exclusive License to Springer Nature Singapore Ltd 2022